Let's say you observe with a radio telescope at some randomly selected positions on the sky for whatever reason. And you expect to measure some radio fluxes. And your expectation is that these measurements should be distributed in some Gaussian way about some true flux density with a variance of sigma squared. And from earlier observations we have a priori, a prior probability distribution that's looking like this, because we were looking it up in some catalog of radio observations. Yeah, that's our prior knowledge. K here makes sure that this is normalized to unity. So that means our likelihood, so given some true flux that's actually emitted, the probability to observe a flux F is this, because we assumed we have some normal distribution around the true value. Like when you do the practica, for example, then you also assume a similar thing. Okay? So that's the likelihood, that's our prior probability. So that means we can compute the posterior probability. So what's the actual true value of S given we observe some data? And we can write this like this. And here, what we did earlier with the integral over the likelihood times the prior and so on and dividing by it, it's all summarized in this K prime variable that makes sure that we normalize to unity. Okay? That's for one measurement. If we have a couple of measurements, then this is the result. And let's assume this is the data that we took. Measurements in some arbitrary units, maybe Jansky. We have a noise level that we can estimate from our detector, and we know the numbers needs to be between 1 and 100 because everything else is physically not possible. Yeah. Then what I compute here, this is our prior probability distribution. That's our expectation before we start our telescope. Yeah, that's the function that I gave on the previous slide. We expect many measurements with low numbers and very few with high numbers. And then we observe two. We turn on our Bayes machine, crank the wheel, compute the posterior probability, and this is the blue curve here. Since our result was this value here, which given our prior seems to be unlikely, the posterior probability is shifted to somewhat higher values. If we get as a second measurement this value, again we crank our integral machine, and now we get here the yellow curve as a result. And we can do this again for the other measurements. Here I have for the first 4 measurements, it becomes like this. For the 5th measurement, it becomes like this. And after 5 measurements, we would say, okay, the expectation value is something like 1.7 or 1.8 with a given confidence interval for the true flux density on the sky. Okay.